Good morning, each and everyone. My name is Karras. Today I will be presenting the paper entitled Expanding Queries with Maximum Likelihood Estimators and Language Models. This is a joint work with my brother and colleague Aristeidis, with Dr. Leonidas Theodorakopoulos, and the professors Ioanna, Giannoukou, and Sioutas. Starting off with the introduction, the query expansion techniques have emerged in our days because in the big data era, we want to less or try to decrease the time to perform queries, and we want to find if a given query is close to what we look for and so on. So they address the issue of term mismatching between a given query Q and a document D they try to target. So there are two families for query expansion techniques. There are the local techniques based on pseudo, relevance, and indirect feedback, and there are the global techniques based on the creation of a dictionary. So in this work we focus on the first category, where only the first scanned documents are deemed as significant. Pseudo-relevant documents in this category are scanned for potential candidate phrases that may aid in expanding a given query Q. Moving to the strategies and motivation, the main idea behind this work is the expansion of the language models, where statistical language models are frequently used in the field of informational retrieval because they have a strong theoretical foundation and they perform well empirically. So two well-known probabilistic approaches that are up-to-date is the Robertson-Spark-Jones model and the Croft and Harper model. So both approaches evaluate the likelihood that each page is relevant to a given query Q. As we can say, the two primary issues are related here to predict both queries and the document models at the same time. So by predicting the factor form of the distribution PQD, where Q represents the query and D the document, a language model determines the relevance of a document D to a given query Q. Let's talk about the problem formulation. As we already said, the goal is to prove the existence of another technique that's capable to extend a query that utilizes the idea of the language model, especially an n-gram model. So to accomplish this purpose, we have to look for the mismatch between the words in the query and the terms in a corpus of documents at the same time. So the likelihood of creating a new Q query given an estimate of the language model for a D document can only be determined by ranking the relevant documents. So this is the first phase in our methodology. We try to rank the documents. So when dealing with big corpus of documents and creating n language models with n equal to the number of documents we have, this proves to be a computationally difficult procedure. So we try to find an optimal way to do so. So the tf-idf recovery model is being utilized in accordance with word weighting, which is something we utilize in this work, which is extensively employed in the informational retrieval area. And this leads to sufficient results, not optimal, but sufficient results to work on for improvements. So the inclusion of the language model and other semantic analytic approaches enabled us to overpass the tf-idf baseline to produce ranking of texts which are more relevant to a given query Q. Moving on to the methodology, as we already said, we first rank the documents. So to rank the documents using weights on the tf-idf model, we use the cosine similarity measure. So the tf-idf technique is given by equation 1. It's a technique widely used in the field of IR, where basically the FTD is the raw count of a term we look for in a document, meaning the number of times the term T occurs in a document D, where the denominator is simply the total number of terms in a document D, where we count each document, each occurrence of the same term separately. So the scope supplied to the target document serves here as a minimal threshold for constructing the new document ranking. So this step is crucial, since if we specify a higher threshold, this would result in the target document being omitted from future computations we might perform later. By lowering the threshold, documents will include noise, and this will affect the results of the system. Therefore, we have to find an optimal threshold so as to create a system that is operates smoothly and robust. Moving on to the language model creation, the language models for each document are generated based on the ranking we previously saw, where n language models with n equal to the number of relevant documents based on the query keywords are created. To do this step, we use the skipgram idea, where we create a step size s equal to 2. Therefore, to avoid a model giving a zero probability to an unseen event, in this case to an unseen query or a term, meaning when a word in the query is not included in the language model, we can remove some probability from common events and apply it to occurrences we have not seen before. So the creation of several language models with step size s with s ranging from the value of 2 up to 10. Next, we perform on each iteration a new ranking of documents using the maximum likelihood estimation between the query Q and its document D, which is shown in equation 2. Basically, we count the weights we created before, the weight minus 1, and on the denominator we count the weight minus 1. So this creates an approximation to rank the documents. We sort the documents based on the ranking we created. So sorting the documents based on the ranks we previously created leads to selecting the most optimal rank calculated by the lambda parameter. So to sort the documents, we use three techniques. We use the Laplace smoothing technique, which is shown in equation 3. We use the maximum likelihood of order 2 or bigrams, which is shown in equation 4. And we use the zerograms calculation, which is shown in equation 5. Where the SI lambda I equals to 1, the MD represents the language model of the single document, the MC represents the language model of the entire collection of documents, and the absolute value of V represents the number of unique words within the corpus of documents. Moving to the smoothing ranking process, we smooth the lambda parameter using a technique as in equation 6. So we'll look for the amount of perplexity between the query word set W, which is basically the set that contains the documents we applied weights into, and then we try to smooth the lambda parameter using this equation. This will serve as an evaluation metric on the experiments. On the experimental results, initially a few words about the dataset summary and the dataset utilized in this work. This was the famous recipes 1 million plus dataset, which is a collection created by the MIT, consisting of more than 1 million recipes. So of all these recipes, we used a subset of approximately 50,000 documents due to their informative content, which basically fits the purpose of this paper. So we try to use a subset for better computations and for faster computations. So to fetch all data from the MIT, we use two APIs, which are named the Scrape Schema Recipe and the USDA. So for the evaluations, we either use one of them or we use a combination among them. And to categorize the documents in ranking categories, we use three different distinct methods. We can say that we have the overestimated category if the uncategorized document is considered as good. We have the underestimated category, where we consider the uncategorized document as not good, and we have the discarded category, where we discard the uncategorized document from the evaluation and from the results. To evaluate the results, we use the precision metric, which is shown in equation 7, where we basically look for relevant documents, retrieved documents, and the denominator, the absolute value of the retrieved documents. So the experimental results as per the precision metric are given here in this table, We can see on the left hand side the queries we performed and the three categories we previously mentioned. The USDA API method and the mixed method, where we basically utilize the scrape and the USDA method to fetch the data. As we can observe, the best precision on each query for each method is given by using the mixed method, where we fetch data using both APIs, where the average precision on all queries was 0.99487, which is, as we can say, a really good result. Moving on to the queries and the outcomes in a graphical representation way. On the left hand side we have the query broccoli, heat, cauliflower, saucepan, soup, remain, recipe, butter. So these are 8 words in a given query. With blue color we have all the documents. With red color we have the target, what we aim to reach, and the star represents the given query. So in this case, this query. And then we calculate this Euclidean distance between the query and the document we target on. On the right hand side we have the query broccoli, cauliflower, soup, recipe. As we can observe, on the left hand side we had 8 words, so more words created less distance, and the query, although it contained some words that are not close to each other, the distance was less, and the query was able to reach the document target with a good approximation as per distance. While on the right hand side the distance was high, and it means that the query should be fed with more words. Moving on to another representation, on the left hand side we have the query cheese, butter, biscuit, which is only 3 words, and as before we can observe the distance is high enough. It's high basically based on the query and the document we target for. While on the right hand side we have cheese 12, butter 4, biscuit 230. So even that we have 5 words where basically 2 words are numbers 12 and 230, the distance lowered, meaning that the model works and the targeting document is the query is closer to the target document. So basically the system looks for ingredients in recipes, and it detects that the 12 and the 230 after the word biscuit means that you try to reach this document here. Moving on to the models we utilize and the distinct libraries which are capable to tokenize documents and queries, we utilize Spacey, Gensim, NLTK, and Karras. So each of them generates results that vary in terms of perplexity, number of queries produced, calculation time, and ranking. Here we have the table containing the document position and the ranking of relevant documents. With T we represent the tf-idf already known method, and with P we represent the proposed method. Here basically the documents are ranked in decreasing way, where we mean that the lowest value the best. So think of a race when someone gets the first position, this is the best place to be. Next up, the second place is still good, but it's not the best. So the lowest value here is the best targeting, is the best position for targeting document. It means that the given query is as close as possible to the document we look for. So as you can see, the P, the proposed method, has low values. Almost everywhere it's zeros, except the Gensim library, which produced a 37 ranking. And in the next table we have the performance in terms of number of queries and the computation time required to perform so. So the Karras library created 15,000 queries in load time, meaning that we refer to load time up to 5 minutes. The NLTK library produced the same number of queries in low time as well, so less than 5 minutes. The Space library produced 20,000 queries in high time, meaning that it required more than 20 minutes. And the Gensim library was the best as per queries with 22,000 queries in medium time, which we refer to up to 15 minutes. Moving on to the Euclidean distance, we use as a metric, and we basically want to look the Euclidean distance between a given query and the target document at a specific perplexity p. We have all the libraries, Karras, NLTK, Spacey, Gensim, and we have the Euclidean distance and the perplexity. What we can observe here, the perplexity, the higher it is, the better. So if we look on Gensim library, the distance is the lowest, not to all values, but at the most columns the distance is the lowest, while the perplexity is the highest compared to, for example, for Spacey, for query 1 the perplexity is 90, here is 34, on the next query is 53, while on Spacey it's 11, and so on. So Gensim was the library that performed best as per Euclidean distance, which means it lowered the query and the targeting document, and the perplexity was the highest, meaning that it performed the best results. So in conclusion, we can say that new queries are generated approximately, and that the Gensim is the library that achieves the best performance, as we previously said. However, some things need improvement, such as defining a way for establishing a suitable threshold for creating each ranking of relevant documents, as we said that in the introduction. Throughout these research, the thresholds applied utilizing the sklearn library precision recall curve function were considered, but not all of them had a sufficient score to examine the target document. So as a result, we decided to take into account the initial threshold, referring to the weights applied to the target document utilizing the cosine similarity approach. Future directions of this work include improvements in the search performance, where we can set an ad hoc barrier that can prevent the ranking of relevant documents from including all of the collections of documents. Another future work is to decrease the term matrix with stochastic gradient descent. Concerning the usage of various parsers, we can also create a hybrid system which will be capable to produce a large number of queries in a short period of time, and moreover it will be really interesting to provide a mechanism which will be capable to extend the initial query with words contained within a vocabulary such as WordNet, Wikipedia, or any other vocabulary. That was pretty much it. Thanks for your attention. If you have any questions, I would be delighted to answer them.